In this video, we're going to look at one of the most popular interpretations of quantum mechanics, the many worlds interpretation. Now, this is one you may have heard of, even if you're not into physics or quantum mechanics in general, because it's been heavily featured in science fiction and popular science, notably in Star Trek and Rick and Morty. The theory was first proposed by Hugh Everett in 1957 and has gained a considerable following since then. In this video, we're going to discuss the basic theory behind the interpretation, its pros and cons, and finally, its philosophical implications. So, in a previous video, we talked about the standard Copenhagen interpretation of quantum mechanics, the one that's in the textbooks, the one they'll generally teach you in uni or college. But as we saw, there are a bunch of problems with it. The many worlds interpretation claims to solve many of these issues, but as we'll see, it also has a few problems of its own. So what does the theory say? Well, in our everyday view of the world, we think of there as being one single version of history. But what the many worlds theory says is that when you make a quantum measurement, every possible outcome of that measurement occurs. And each outcome occurs in a separate universe within a wider multiverse. If you scale that idea up, what this theory implies is that there are an almost infinite number of universes, each containing a separate version of reality, and also that every possible version of reality that could occur is contained in these universes. In this interpretation, the wave function is actually real, unlike in the Copenhagen interpretation, where its definition was pretty vague. Measurement is explained by what is known as quantum decoherence, which occurs when the quantum states interact with the environment, producing quantum entanglement between the observer and the measurement, and splitting the universe into mutually unobservable alternate histories. The many worlds interpretation obviously solves many of the problems with the Copenhagen interpretation. Most significantly, it gets rid of the idea of wave function collapse, which was never particularly well defined in the Copenhagen interpretation. The idea of the wave function collapsing never really had any mathematical basis and was pretty much created artificially to plug the holes in the theory. But in the many worlds theory, there's no collapse at all, as every possible outcome of events occurs in a separate universe. Another major advantage of the many worlds theory is that it doesn't rely on the idea of there being an external observer to make it work, as the quantum decoherence will occur whether or not there is an observer. The theory also resolves most of the familiar paradoxes associated with quantum mechanics. For example, in the Schrödinger's cat paradox, where a cat is placed inside a box containing an unstable nucleus, whose potential decay would trigger the release of lethal poison. If we followed the Copenhagen interpretation, the cat would be simultaneously dead and alive before the box is opened. However, if we followed the many worlds interpretation, the cat would be dead in one universe and alive in another. So when we open the box, we essentially find out which universe we're in, thus resolving the paradox. Some people claim the many worlds interpretation is more a theory than an interpretation because it makes testable predictions and therefore can be falsified, although this is currently debated. The lack of a collapse leads to effects which we could measure. However, to measure this, we would require more advanced technology, which would allow us to undo a quantum experiment, which would include the ability to reverse the detection process. Needless to say, something like this isn't on the horizon anytime soon. Another way we could try to falsify the theory is to run an interference experiment with macroscopic bodies, and so detect an interference between parallel universes. The reason we need macroscopic bodies is because two universes are only considered different if they contain at least one macroscopic object with different macroscopic states. However, here again we run into a problem, because there is currently no way of detecting interference between macroscopic bodies. Of course, there have been many criticisms of this theory. First of all, there have been complaints about the language and terminology used in the theory. For example, the word measurement is used regularly when describing the many worlds interpretation, but it's never really well defined. Supporters of the theory argue that in reality measurements are just a subclass of interaction, so there's nothing special to define about measurements at all. On top of that, there are more serious problems with the many worlds theory. A major philosophical idea which apparently comes down against the many worlds theory is the idea of Occam's razor, which states that when deciding which of two possible theories better explains a phenomenon, you should always choose the simplest possible theory. The many worlds theory, with its multiple universes, certainly appears more complex than the Copenhagen interpretation. But, on the other hand, the many worlds theory contains less formal structure than the Copenhagen interpretation, and so in that sense is much more streamlined, satisfying Occam's razor. Finally, one of the more abstract and philosophical criticisms of the theory is that someone who wholeheartedly believed in the theory would act in an irrational manner. For example, imagine this scenario. You're invited to play a game of Russian roulette, where the reward for winning is becoming a millionaire, and the penalty for losing is death. The argument here is that if you genuinely believe in the many worlds interpretation, you would always agree to play the game, even if the chances of winning are 1 in 1,000. This is because you know that in one universe out of 1,000 you will win and take the prize money, even if in the other 999 you die. Therefore, you would agree to take part in this ridiculous game. However, the counter-argument offered is that you should avoid playing the game because the number of universes in which you end up dead will be much greater than the number which you end up alive in. So, in other words, you should care about what will happen in every universe and not just the fact that you will survive and become a millionaire in one universe. Does this mean that we have a responsibility to all future versions of ourselves in every universe? If you accept this responsibility, then you can justify believing in the many worlds interpretation, while still behaving as you would if you believed in the standard Copenhagen interpretation. So now for the final part of this video, we're going to discuss the philosophical implications which stem from the many worlds theory. If we accept it as true, then we must accept that there are a near infinite number of universes which contain every possible outcome of reality. There are parallel universes of you and me leading similar but different lives. This seriously undermines all our deeply held ideas about a sense of self. After all, if there are multiple different versions of me, who am I? Proponents of the theory would suggest that you are in fact the sum total of all the different outcomes of your life, spread throughout the multiverse. But if the universes are totally separate and unable to communicate with each other, how can there be any sense of self that spans across these universes? That's why some proponents of the theory actually say that there is no sense of self, that there is no I, since this would only make sense if your identity was confined to a single universe. Is this abolition of a sense of self too much to accept? Do the pros of the many worlds interpretation outweigh its cons? It is unlikely that there will be a consensus anytime soon. Make sure to like and subscribe if you enjoyed this video, and from the whole team, thanks for watching.